So what are some properties of our esters? Like I showed you before, that's another way we can write an ester. It's going to be less polar and less soluble in water and have a lower melting point and a lower boiling point than carboxylic acids. Well, what's the reason why? Look at the fact that your carboxylic acid can hydrogen bond. Bond. Your ester, because it's found in the middle of a molecule, not on the end, it doesn't have the ability for that oxygen to hydrogen bond. So as a result, we're going to see that it's not going to be as soluble. It doesn't have that hydrogen bonding ability, so less melting and boiling point as well compared to carboxylic acids. Your low molecular mass esters are going to be detectable by scent. So those are the ones that we see in perfumes, and as a result can be gases as well because they are very lightweight. Our larger, heavier esters are going to commonly be found as waxes. So again, just showing you that the smaller they are, the lighter they're going to be, and then they can move around and be sensed more easily. So if you can make an ester, can we reverse our reaction and break apart our ester? Yes, and those reactions are called hydrolysis reactions. So when esters are treated with an acid or base, a reversal of an esterification reaction occurs. So basically your ester is split up into its acid and specifically its alcohol components. So this process is called saponification. The reason why they named it saponification is because one of the products is actually used to make soap. So here is our ester. So what's going to happen here is you're going to have an ester and an acid or base. Pretty much all our reactions involve a base for some odd reason. So you have sodium hydroxide as a strong base. So what's going to happen here is it's going to break the ester apart into two different things. So you have sodium, which is a plus one, and a hydroxide, which is a negative. So if we break this apart right here, the oxygen loses a bond. So it becomes negative, and the alcohol group is going to be able to then balance that negative. So it's going to be positive, and it's going to attach to the negative ion here. So this becomes negative, this becomes positive. Well, what happens is your sodium wants to attract to the negative, and your negative here wants to attach to the R group. So this is what you get on this side. You get a sodium salt here, an acid salt. So you can see that it's like almost like a carboxylic acid. It doesn't have the hydrogen. And then the OH group gets attached to the rest of that molecule. So that's going to produce an alcohol. Water molecules will do something very similar again. So here, let's say we have the same thing, but if you have like water, HOH. So this is more clearly how you could see the acid and the alcohol regenerating itself. So your bond is going to break. Again, this is negative. This is going to be positive if that bond breaks. So remember, hydrogen is positive, hydroxide is negative. So your hydrogen is going to get wanted to add to the oxygen. So that's going to produce our carboxylic acid that we've seen before. And the OH gets added to the R. So that's going to produce your alcohol. So whether you see it like this or like this, the reaction's still considered a hydrolysis. So you're breaking apart that molecule here. And the reason why it's called hydrolysis is because you can use water to break that apart. So like I mentioned before, the sodium salt that forms right here is actually going to result in soap. So that's how we make soap. That's why it's called saponification. And it's classified as a hydrolysis as well. So here we want to write a balanced equation for the hydrolysis of ethyl methanoate. So you should be able to look at the ending and say, hey, that's an ester with the O8 ending. So what I would recommend is start by drawing out what that ester is. So I have my carbon double bonded to the oxygen and an oxygen there. So the ethyl group is off of the oxygen. So I'm going to go 1, 2 for an ethyl. And methanoate means that my carboxylic acid end, this side has 1 carbon. So I only need this 1 carbon. So this carbon then needs to have a hydrogen, because if it's only 1 carbon, it has 4 bonds. So that last one should be the hydrogen. So if I'm trying to undergo a hydrolysis, that means I technically would have added, let's say, sodium hydroxide. So we're going to go back and identify that this bond is going to break. The sodium gets added to the oxygen, and the rest of our molecule gets the OH. So I would have ended up with the sodium. Sometimes I'll put in the negatives and the positives, you don't have to. And I'm also going to get the ethyl group. And I'm going to get that attached to the alcohol. So here is the ethyl group attached to the alcohol. If you chose instead to do water, hydrolysis, that's fine. So I'm going to draw the same product, reactant here. So if I instead decided to react it with water for hydrolysis, HOH, the same idea is that your bond gets broken, your hydrogen gets added to this to make our carboxylic acid, the hydroxyl gets added to this side right here. So that's going to form, more specifically now, so you could see it, the carboxylic acid and the alcohol. So it's ethyl, and so same products. So this is the salt, sodium salts. This more specifically is the carboxylic acid. So homework for today, there is an exit card. So if you can make sure that you complete it and hand it in by the end of class. And then also you have your reactions worksheet.